Welcome to Spring LIB.
We are given these two half reactions that take place within a galvanic cell, and we want to find the value for the change in Gibbs free energy reaction at standard conditions, as well as the equilibrium constant K. We know that this is a galvanic cell, and so therefore the overall cell potential at standard conditions has to come out to a positive value. So in order to rearrange these equations, in order to cancel out the total number of electrons on each side while also giving a positive cell potential, we have to keep the reaction with the greater value for the standard reduction potential to be the reaction that undergoes reduction and reverse the other reaction to undergo oxidation. And so that means that this second reaction we have to reverse and also reverse the sign of the standard reduction potential. And when we do that and combine the equations, we see that we need to multiply the top equation by 3 and the bottom equation by 4, so we cancel off 12 total electrons on each side. And so we are left with 3m 4 plus aqueous plus 4n solid goes to 3m solid plus 4n 3 plus aqueous. And when we add the two potentials together to find the overall cell potential at standard conditions, we see that it comes out to 0.27 volts. Now we can use that value to solve for delta G at standard conditions. So delta G is equal to negative N F E. N we saw was 12 moles of electrons. F is Faraday's constant of 96,485 coulombs per mole of electrons times 0.27 joules per coulomb. And so delta G at standard conditions, when we calculate that out, we get it in units of joules, and we can convert it into kilojoules. And that should come out to about negative 310 kilojoules. And now to find the value of K, the equilibrium constant, we use a Nernst equation. We know that at equilibrium, the cell potential is equal to 0. And this is equal to the standard cell potential, which we found to be 0.27 volts, minus 0.0591 over n, which we saw before is equal to 12, times the log of K. Now we rearrange this equation and solve for K, and we should get K to be equal to about 6.6 times 10 to the power of 54.